Is it just me?
Hello? Is it better now?
Yeah, you'll have to keep your mic close.
Okay, fine. I'll do that.
You have another pair of microphones which you can use?
No, sir, this is the only one.
Then you will have to keep it close to your mouth.
Yeah.
All right. All yours, Manoranjan.
Yes, sir. Can you see my screen, sir?
Yes, I can see your screen.
Yeah, so good afternoon everyone. I'm Manoranjan and today I'm working on the project on hydrodynamic object detection using neural networks. Uh, this will be my second presentation, so I'm thinking of giving a small recap and then what is the progress since the last meeting and what are left in the current project. So, as a recap, the aim of the project is to determine the shape, size, and location of the 3D object in water. And do note that I'm not using any cameras or visual systems here, and it's rather the velocity or pressure values that are detected from the sensors that which in the sensors are kind of present uh, in downstream of that object in water. So for the current project, I will be using the analytical results from potential theory for getting those velocity and pressure and see how the system works. And later we'll be trying to implement in a practical situation. So for relating the velocity and pressure values, I will be using artificial neural networks that tries to relate these velocity and pressure points to the shape descriptors. So these descriptors characterize the shape of the 3D object, and I'll try to discuss on depth on what is meant by these shape descriptors in this presentation. Okay, so these are the overview of my major tasks in the project. So I find a harmonic map onto a sphere for 3D objects as we discussed in the previous presentation. And from that I compute the shape descriptors. And after that I make the descriptor rotation invariant as we discussed that so the main idea of making this rotation invariant, to remind once again, is that the different orientation of the same object will result in different shape descriptors. So to nullify that effect, uh, I have to follow some methods which makes it rotation invariant, so that for the same object I will have similar coefficients. Then I'll be trying to build an artificial neural network which takes these flow data, like I've discussed in the previous slide, and I predict the shape descriptors. And once I have the shape descriptors, I can reconstruct the object graph. So this flowchart that you see here can give you a better idea of what my project is, the overall structure. So this can be the 3D object. For in this current case, we can consider a submarine. And these three spheres that you see here are in the process of mapping the submarine to a harmonic sphere. So as we discussed in the previous presentation, these correspond to the intermediate steps, these two spheres, and this will be the final harmonic sphere. So from the harmonic sphere, what are we going to do? We are going to calculate the shape descriptors. And from the once we have these descriptors, we can reconstruct the shape graph. So once we have the neural network ready, we will be obtaining. Is there any issue?
I think there is a question.
Okay.
And the question is, Mansi, you can unmute your microphone and ask.
All right, sir. No, so I was not present in the presentation which you gave before, but I wanted to know how harmonic maps are constructed.
Okay, so that involves that harmonic map algorithm is a long process actually. We'll have 3 to 4 steps for, I mean, there are two algorithms inside computing harmonic map algorithm in itself. So to give you a small idea, so what I'll be doing is this submarine. I first compute something called as Gauss map, or another. You can also take it as a star map. So what I'll do is I first normalize the unit vector, normalize the vectors that represents this submarine. So the submarine will be represented by different vertices, right? So this is a 3D object. So it will be represented by different vertices as a mesh file. So I normalize these by compute. I mean, I first compute its center and then normalize these vectors. That then what it will do is it will map it to a sphere like this. But this will have a lot of overlaps. And in fact, you can see in this picture that the sail of the submarine is mapped here. So now the subsequent process in this harmonic map will be to smoothen this star map out. So there is some mathematical calculations behind it. So I try to smoothen this sphere out, and this will be my Tourette map. There is something called as Tourette map in the intermediate state, and further making them smooth, you will get a harmonic map. So the basic idea of harmonic map is that each of these vertices that are present in the submarine will have a unique vertex that represent in the harmonic map. Is that fine? I may not be able to tell you the mathematical expressions currently because that may itself take some time. But this is the qualitative view of this mapping.
No, this is super helpful. I think I got a fair idea.
Okay. Fine.
Thank you.
Okay, so moving on. So once I build, so for the neural network, I'll be getting inputs from the velocity or pressure values, and this will be my input to a neural network, and the output from it will be the descriptors. So once I have the descriptors, as I explained before, you can get the submarine back or whatever object it is, we can get it back. So we should train this for several of these data. That's the overall view. So the next, so this equation that you see here is what we discussed as the equation that helps me in calculating the harmonic coefficients, spherical harmonic coefficients. And this spherical harmonic coefficient is what I call as the shape descriptors. So the CLM that you see here will act as my shape descriptors. So to go more deep into this expression, so YLM that you see on this equation is the spherical harmonic function, and this x theta comma phi will be represented by xyz. So what is this xyz is? To give you a recap, so consider, as I've discussed before, all the vertices on this sphere will map to some point on the submarine, right? So this point, so if I consider this particular point, say, so consider it maps to this point somewhere here. So whatever the value of xyz in this original mesh, this original submarine, will be my left-hand side of this equation. And YLM theta comma phi, that is the spherical harmonic function, this value, particular value, will be given by the theta comma phi, this vector. So the theta comma phi will be from this particular vertex that you see on the sphere. And since you have this YLM theta comma phi and x theta comma phi as known, your unknown will be the CLM, which you have to solve these equations. So there will be multiple vertices for the submarine, right? So we have to solve these equations simultaneously. So we can use this least squares method, so several methods. So from that we can calculate the CLM. And another point to note here is L is equal to 0. So each L value will have 2L plus 1 M values, and we can control the up to how much L we want the descriptors to be. So this is where we can control the shape description. To speak more upon this coefficients, this coefficient of L is equal to 0, that is C00, that will represent the translation of the submarine in the original frame, original reference frame. And this coefficient of L is equal to 1 will approximate the shape as an ellipsoid. So if you consider only L is equal, if you consider up to L is equal to 1, so there will be 4 coefficients. So one is L is equal to 0. For L is equal to 1, you will have three coefficients in particular, because it will go from M is equal to -1 to 1. So now you will have four coefficients in total, and that will approximate the shape as an ellipsoid. And once you add on further L is equal to 2, L is equal to 3, you will get a better description of the shape. And these pictures you see here can give you a better idea of how using different, limiting the coefficients will describe the shape. So this particular shape that you see here, it corresponds to L is equal to 0, I mean L is equal to 1. And as you can see, it approximates this submarine as an ellipsoid. And after that, if this is corresponding to L is equal to 10. And you can see here that now an extra feature of this sail of the submarine is added here. And once I increase the L up, once I increase up to 30, you will get a really good approximation of the shape. This is just for representation, but yes. So this L is equal to 30 will give you a very good approximation of the shape. So
the last one is how much L?
This is L is equal to 30, sir. 30
coefficient.
Yeah.
Okay,
Yeah.
30 L.
Yeah.
And that corresponds to about how many coefficients in
31 square. 31 square. About
31 square.
Yeah.
Okay, all right, above 900 coefficients.
Yeah.
Okay.
This will be like a trade-off. So once you increase the coefficients, you will have to your computation cost will be more, and that we can, since we can limit upon it, once we get a better approximation of the shape, you can. That's up to us to decide how much we want to represent the shape. That's the basic idea so far. So moving on. So up to this.
Hello.
Yes.
Can you explain that y in the equation? I didn't understand that.
Okay, so this YLM is something called a spherical harmonic equation. So if you have taken this differential equation course from our maths department, you would have studied this YLM spirit. So it's just a function, okay? So you will okay, I have a function, yeah. So y1 minus 1 will be represented by this equation, something like that.
Okay.
Right? So
you can think of them as basis functions. So
Yeah.
for example, in your Fourier analysis, your basis functions are sine and cosine, right? Sine of pi, sine of 2 omega, sine of 3 omega, so on and so forth. So similarly, in a spherical geometry representation, you can think of these as basis functions, which are extending all the way from y 0, 0, y minus 1, 1, 1, y 1, 0, so on and so forth. So
Yes,
these are coefficients which are going to map something in the spherical domain. It is difficult to give probably a physical understanding of what they exactly look like, although there are pictures which do show that upon, and maybe Manoranjan, next time you can include some of those pictures into the presentation.
Yes,
but you can think of them as basis functions just like sine or cosine. And they have a specific form, which is what he was showing, the mathematical expressions for some of them. So they are all well-defined functions. And now the objective is how much of each function adds up together to give you the final geometry is determined by that weighting factor, which is your CLM. So how are these spherical bases weighted together to form the complete geometry is what he's trying to demarcate into. So like you saw, L equal to 1 represents an ellipsoid, right? So your submarine can be represented on a broad shape by what sort of an ellipsoid? Then how do I perturb the ellipsoid further and add more local features to it? That is what you see in the middle picture. And finally, you add more and more and more local features, you will get the picture on the right.
Yes, sir. Like if we take many coefficients, then we'll get the accurate one.
Yes.
Accurate. Yes.
Correct.
Okay.
So the beauty of this process is rightly as you pointed out, is that it is structured in such a manner that the geometry that you are adding at every L level, okay, as L increases, the features that you are adding are more and more local and not global.
Yes, sir. Yes.
Okay, and that's the beauty of the process, that if I truncate it at some value and I say I'll only consider up to L equal to 10, then whatever I am losing is the local features after that. So otherwise what happens if that such an ordering was not there, and let us say that L equal to 5 was the most relevant and L equal to 4 is where I truncated, then I'll get complete garbage as the output from the program. Right? The shape will not be necessarily be representing anything in general.
Yes, sir. Yes.
So that's the beauty of the process, that it can organize them in a descending order of priority using these spherical functions.
Yes, sir.
But good question. Any other thoughts, questions which is not clear? It's a good time to ask him now.
So like these 900 coefficients that like finally we will get, those will be like those we will have to predict, right?
Kind of. I mean, that's we have to see whether we can stop it before that. But
like,
actually,
whatever
if we,
you suggest.
yeah, I mean, whatever that coefficient is, we kind of have to pick. But there is a symmetry between this coefficient, which we can use it to our advantage and predict a lesser numbers also. So, for example, yeah, so this C minus 1, 1 and C1 minus 1 and C1, 1. So, for M, so if you consider this for L is equal to 1 itself, uh, the coefficient corresponding to M is equal to minus 1 and M is equal to 1 will be related in a way. That relation, if I am not wrong, is given by some minus 1 to the power M. So it's like CL minus M is equal to CL minus 1 to the power M CLM. So there is a relation between this coefficient itself. So we can use that particular part and we can try to predict lesser coefficients, and from that we can use get the other coefficients.
Okay.
Yeah, I think I should have mentioned that as well, the relation, but yes.
So like say if L is equal to 1, so so M is equal to 0 and M equal to 1, or maybe those only those two we will
Yes,
need,
sort
and
of.
minus
Correct,
1 we
correct.
won't need.
Yes,
Okay.
minus 1. Correct.
Okay.
So any other questions? Fine.
Yeah,
If
looks
not-
like you can go ahead.
Yes, sir. Okay, so now at the last presentation, I have left at the point where my challenge was in the where my challenge was to see how I can make the coefficients rotation invariant. So as I've discussed before, this rotation invariant, different orientations of the 3D object will lead to different coefficients. So to make that, to nullify that, so I have to make that object. We were lastly we were trying to rotate them to a canonical orientation. So canonical orientation means so all objects. I mean the different orientation of the same object. What I try to do is I try to rotate it to a canonical orientation, which means some fixed orientation based upon the geometry of that particular object. So to give you
Why is this rotation invariance needed particularly?
rotation invariance is required because like different. So let me show. Go to this slide. So this is a particular submarine which consider that it's oriented along the x direction, this main axis. So if there is another submarine which is oriented along the y axis, then what will happen is this process will lead to a different coefficients. But I want the same object, I mean, I want that object to be represented by the same coefficient, at least similar coefficients, so that I can get I will be able to reconstruct the shape back again. If not, what will happen is this will lead to considering that different coefficients will lead to considering that that is a separate object in itself. So yes,
So the idea here is that if you have a same object in a different orientation, but the flow direction remains the same, you still want to be able to predict that it is the same object from your neural network. Correct?
Yeah.
So that what happens is if you can convert them into a canonical orientation, so no matter how that object is oriented in the flow, you are trying to make your neural network at the end of the day learn that it should still predict it to be that object only.
Yeah.
Yeah.
So yeah.
So yesterday in the review meeting, you said that like you will be measuring the flow in the wake of the vessel.
Behind the vessel, yeah. I mean, behind the.
So when you're going to do that, like it is always in that orientation, right? So why do you need this rotational invariance?
No, I mean, wake in the if there is a flow and the object is stationary, consider that it's stationary, then I'll be keeping that. Say I'll have a sensor behind that in the downstream of that flow. So basically, it's like we are keeping the sensors downstream of this flow.
Okay, so you need not always measure it right behind the vehicle.
It's not like right behind the vehicle. It's like the downstream of the flow, to be more precise.
Okay, and if the flow is coming from the lateral, like sideways, you will measure in this on the side of the vehicle, not behind.
Right. Correct. Yes.
So the problem is much more like the practical problem will be much more complicated than the one which he is attempting. But what we want to do is he wants to look at a smaller version of the problem and see whether we can actually demonstrate a proof of concept and then later on extend it. So you can think of it as the flow will always be coming. So in reality, what is happening, your object is moving. It's not that the flow is coming in a certain direction. Your object is moving in different directions. So you have a sensor points, let's say, which are located at a fixed location. And then your submarine may be going in different orientations around it. The question is, by using the pressure measurements, can we figure out what is the shape of the fellow who went by us? Is that making sense? Yeah.
Yes.
In reality, there is no requirement that the submarine should go in a straight line, first of all. It can take any sort of a path. But then it becomes much more challenging to solve such problems at the outset. So we are assuming that the submarine is going in a straight line, which may not be aligned with the axis in which we have placed sensors. Right? So it may be at an angle to the sensors which we have placed. It may be at an angle that it may be moving. So that I can equivalently consider, or we can equivalently consider as if the flow is coming in one direction, but the object is at an angle.
Yeah, got it.
Okay, all right.
Yeah, so, okay, so to discuss more upon how the coefficients, to give a better idea of how the coefficients varies and what are the factors that it depends on. These coefficients, that is the spherical harmonic coefficients that you saw, CLMs, depends upon the orientation of the object in space. So you can consider that as the object space, that is the actual frame in which the object is in. And another aspect is something called as parameter space. So you can consider that parameter space as this sphere that we have mapped to. So what in essence is happening is, to give a better idea. So consider this point. So if you consider this a vertex somewhere here, if I rotate this harmonic sphere, if I rotate this sphere, assume that it's the point somewhere, the point here comes somewhere here, comes to somewhere here. Okay, but the vertex that is represented even after rotation in the original space will remain the same, right? So any rotations on this harmonic sphere will not result in the rotation in the object space. However, when you want to compare two different objects coefficient, two objects coefficients, it has to be aligned both in the harmonic sphere, in the parameter space, as well as the object space. So what in essence is, this was the point I left. I was not able to figure out in the last meeting, last presentation. So the coefficients also depend on this parameter space, and we have to align in both the object space and the parameter space. So if the harmonic sphere is not oriented, then in that case also the coefficients will be different, and and if the object is differently oriented, in that case also the coefficient is different. And we should make both of them align to a canonical orientation before we make this. And if we make that, if we do that, then the coefficients that we get will be rotation invariants. Is that point understood, or should I explain it once more? To give you a better, this example that you see here, I can explain that more on this as well. So this is say this is A and B are two different objects. So in some way I say align this B to C. So now both A and C are similarly aligned in the original space. So this is from a paper on different paper on modeling three-dimensional morphological structure using spherical harmonics. They are using a different method. They first align it in the object space by using something called as landmarks. I was not that much interested in the method they are using, but just to give you an example, they so this particular so these two objects are now aligned to a similar orientation. However, in the parameter space, it is not necessary. That is, once you map it to a harmonic sphere, it is not necessary that both of them will be similarly aligned. So this color, this color in the down pictures down that you see. So this D picture that you see corresponds to the parameter space of A, and this E picture that you see corresponds to the parameter space of C, and both their both their parameter space values will be different. So the idea here is, if you see in this previous equation, this YLM theta comma phi will be different. So, however, even though x comma theta comma phi is the same, YLM theta comma phi will be different, and this will change. So that's the basic idea here, and we have to uh, um, like do some methods, work on methods to bring this parameter space to you have to align this parameter space as well. And once this is aligned, as you can see, these are characterized by the color in this picture, and once this is aligned, then you can compare both the picture and see, both the objects, and see how they are related to. Am I clear, or is there any issues? Because the further slides I will be discussing will be more upon how I am doing this.
Yeah, Manoranjan.
Yeah.
How would you exactly be determining the baseline alignment, in the sense that you said that the B figure should be matching with A figure, the alignment, right?
That I will be discussing in the coming slides.
Okay.
So in this picture, in this paper that I have shown, they are manually trying to orient the object in a space, but that may not be suitable for our case. So I'll be discussing upon a method in which we first orient it on the parameter space, and from that I'll be going to the object space.
Okay.
So the thing is, if I am understanding this correctly, and let's say that I have a submarine and I want to compare it with another submarine whose coefficients I already know,
Yeah.
right? So then
Yes.
I have to make sure that the mast of the submarine 1 is aligned with the mast of the submarine 2 before I can make an alignment happen. And that is what is object space alignment.
Yes.
That is what you mean by object space alignment.
Yeah.
The other alignment is if I map both the submarines onto a harmonic sphere, they may not, their mass may not come to the exact same location, and I have to make sure that their mass come to the same location in the harmonic sphere as well, and that is what you are calling as a parameter space rotation.
Correct. Yeah.
Right?
Yes.
Got it.
All right. Any other questions? All right, let's go forward.
So
like that. Sorry. The standard, like, and I don't know to call it standard or not, but in the parameter space, like will it be following certain property for the submarines, like certain property will be followed and all of them will be with respect to that property, like I can't
you
say.
mean, yeah, you can. I think what you mean to say is from the parameter space. Do you mean to ask whether uh, it can characterize some property of the submarine, or do you mean? Yeah, these actually from these coefficients we'll be able to see how the submarine. We can get an idea of how the submarine is oriented and how to rotate it back. So that part I'll be discussing. Do you mean to ask that, or I
Yeah.
Okay. Okay. Okay, so one, if the previous thing is understood, now I'll be discussing upon the method by which I've followed. So this is based on the paper on surface parameterization for 3D description. It came out in the year 1994, and there they are discussing 3 rotations in parameter space and 3 rotations in object space, and they call this method as the first order ellipsoid method. So here what we'll be doing is we'll be considering the coefficients up to L is equal to 1. I mean, not up to, it's the coefficients of L is equal to 1. So you will have 3 coefficients for particular, I mean, this x1 that you see is a vector of x, y, z values, right? So for each of x, y, and z values, you will have 3 coefficients. So you will have 9 coefficients in total. And so these, as I told before, this y1m, so y1 minus 1, this is represented by this equation. And you can also represent this theta comma phi as x comma y. So I rewrite this particular equation in terms of Cartesian coordinates, that is by these expressions that you see here. And I collect the terms of x, y, and z. And I call this matrix as A. So this will be characterized by those coefficients that you see. And each of these coefficients will be a vector of size 3. So this A matrix will be a 3 cross 3 matrix. And in the paper, what they have told is, so once I compute the A transpose A and get the eigenvectors and eigenvalues of this corresponding computation, the roots of the eigenvalues will represent half the length of that main axis of ellipsoid. So what they mean is the eigenvalues of that matrix that we saw will represent the length of these major axis of the submarine. So I mean half the length of the major axis of this ellipsoid. So this it one of the eigenvalues, it will represent this length, and the y, z, and x half lengths. So once you get that, the corresponding eigenvectors will form the rotation matrix. So the rotation matrix will be formed by the corresponding eigenvectors of this particular matrix. And once I get that eigen matrix, once I get the rotation matrix, for each vertex in the harmonic sphere, I use this rotation matrix to rotate it to a particular point. And what this will do is, it will align the parameter space to a canonical orient. You can consider that, for example, canonical orientation. So the new coefficient matrix now, that is the A matrix you saw before, will now change to this A dash, A prime. So this will be, so this A prime, we will be using it for our rotation matrix in the object space. So to give you, and note that one particular point to note is that we are not using information from the higher degrees, that is higher values of L. So what happens is, as you can see, the ellipsoid, once this ellipsoid will not have the that means it will not have additional features, right? So that it will not consider that aspect during the rotation. So what will happen is, there will be a reflection problem. So I'll be discussing that, what problem I'm facing. So what happens is, even though the object will be properly aligned, there will be a flip or a reflection in one of the axes. So I can, so before moving to that part, this rotation in the parameter space will lead to similar orientations in the, canonical orientation in the objects in the parameter space. So this three harmonic sphere that you see on the top is actually the spheres that corresponds to 45-degree orientation with the x-axis, 90-degree orientation, and 135-degree orientation. So after I apply the rotation matrix, if you see these two, 90-degree and 135-degree, you can see that both their harmonic spheres have now become very similar. On the other hand, this 45-degree, I'm not sure whether you can see this, but this 45-degree will actually be flipped. So what even this part will be coming on this side. On this side in this harmonic sphere. Actually, yeah.
1 second. Okay, so I'm just trying to make this explicitly clear for everybody. So the first picture on the top left,
Yes,
that corresponds to a harmonic map where the submarine's longitudinal direction is oriented at 45 degrees to the x-axis.
Yes, correct. Yes, sir.
And then we form the harmonic map from it. Correct. And then you are applying a rotation in the parameter space in order to get the picture on the below.
Correct.
Which is that what you have just now discussed about finding the A matrix, taking A transpose A, and then finding the corresponding eigenvectors to form the rotation matrix in the parameter space.
Yes.
So you are basically rotating this sphere by that rotation matrix.
Correct. Yes.
And that yields the bottom picture.
Yes, sir.
The second picture here on the top presents where the x-axis of the submarine is oriented at 90 degrees to the x-axis in the object space, in the original condition.
Yes, sir.
Right? From there you take a harmonic map, this is what you get. Again, you perform the same process of taking A transpose A and then find the eigenvectors and rotate this sphere, and it will come and give you what is there on the bottom.
Correct.
The same you apply again for 135 degrees rotation as well.
Yes.
And what happens is, once you apply the rotation, the 90 and the 135 in the parameter space are oriented in the same way.
Yes, correct.
So which means that if I now use these three spheres and try to reconstruct the original object, in the second and the third case, the object will still be at object space. When I do the reconstruction, they'll still be looking different.
Correct. Yeah, there will be a reflection. Yes.
But however, when I put them into the harmonic map, they will be looking the same in the harmonic space.
Actually, in the harmonic space,
this one will be different. 45 will be different.
45 will be
90
different.
and 135 will be the same.
Correct. Yes, sir. Yeah.
Okay.
And this result is because we have considered values up to degree L is equal to, I mean, consider the value coefficients of L is equal to 1 to get these rotation matrices. So is that idea clear so far?
So like considering more coefficients, does that
That is,
the
that
A
should,
matrix contains more information?
actually that's what the paper is telling, and yeah, I will be discussing it. But the papers that I have looked at, they have all been telling that if you consider more degrees, you will be able to resolve this issue. But how to do that, I have not been able to find results for that yet, because when you move to higher degrees, you'll be considering more coefficients, and how to use that to consider the A matrix, that is the rotation matrix, is still not very clear. So that's the challenge that I'm facing, and I'm still working on that actually.
Okay.
Okay, so once this is rotated on the parameter space, then the next step is to rotate it on the object space. So the A prime the matrix that I've considered before, that one I normalize the columns of those A prime matrix, and that will result in my RXYZ, that is the rotation matrix that I have to use for object space orientation. And for this, I directly rotate I can directly rotate these coefficients. So I will have the old coefficients, and from these I will get the new coefficient. And as I told you before, this coefficient is of size 3, and each will represent x, y, z values, each of these. So once these coefficients are changed, how when I'm reconstructing it back, I'll show you, I'll show you the pictures. So this submarine that you see will, once I reconstruct it, it will be oriented along the x-axis. So the basic idea behind this first order ellipsoid is it will bring the largest axis orient along the x-axis, and the shorter axis along the y-axis. Yeah, y-axis. And so what is happening now is, since it didn't consider this the
1 second, Manoranjan. I thought the longest along the X, the shortest along the Z, and the intermediate along the Y, right?
Correct.
Okay. Yeah.
So yeah, so these results. So this particular submarine is oriented 45 degree along the x-axis. This is 135 degree with the x-axis. I mean, this is 45 with the x-axis, 135 with the x-axis. If I reconstruct it back, what happens is you can see there is a flip here. I mean, there is a reflection here. So this is the problem that I'm currently facing, and I have to make sure that this is all, both these. Similarly, if I reconstruct it for 90 degrees, it will result in this orientation after the rotations. So I have to make sure that this is not there. I mean, the reflection part should not be there, and I should make them reflection invariants as well. And as I told you before, including information from the higher degrees, they claim that this will sort this issue out, but it has been quite challenging to find the information regarding that. And moreover, like in whatever papers I have seen, many papers try to have a template, and they try to keep the template as the orientation, and they try to make all the other orientations go to the template. So but I don't want something like that, but rather to use it, I mean, compute it automatically from these coefficients, and that's what I'm is left in this part. And after that, I will be computing the velocity and pressure values from potential theory. And once I have these two data ready, I'll be training my artificial neural network, and I'll see how the predictions are and how I can reconstruct it back. So that's it. Thank you.
Thank you, Manoranjan. That was a good presentation. Any questions? Any lingering questions? Now is the time to ask him, and he'll be happy to answer.
Yeah, Manoranjan, could you
Yes.
please put a light on like how you would be using artificial neural networks in order to like define the
Yeah.
shape of an object? Like in the
So
sense that what would be the input, what would be the output, and what all data you would be having?
okay. So the input to my artificial neural network will be the pressure and velocity values. So
Okay.
that I should so assume that a sensor is somewhere here behind the submarine. So whatever values that I detect of the velocity, that is not fully clear yet. It will be mostly velocity and pressure values that I detect from the sensors, and that will be my input to my neural network. So
Okay.
based on the neural network will try to relate this velocity and pressure values to predict the shape descriptors.
Okay. So you mean the
So
parameter values?
yeah, so the CLM that you saw in this equation is what I will be trying to predict.
Okay.
So once
So
I have that CLM, I know right YLM theta comma phi will just be like my grid. So I can, for example, sample the sphere at equal intervals, and that will lead to my grid. And based on that YLM theta comma phi, I will have the CLM, and when I multiply both of them, I will be able to get the XYZ values in the original sphere. That's the basic idea. I mean, the original space.
okay, okay. So my next question was like, how would you be getting the data for the neural network?
Data, yes, I have to consider. So currently, for what I've been discussing with Sir is like for collecting those velocity and pressure values, I have to solve it analytically using potential theory. So I'll so the idea is I'll be using the submarine in a flow and see how it's called as panel method if I'm not wrong. So how different panels will affect the flow I'll see and take a cumulative effect of it, and that will in a particular at a particular distance from like it will be like the place where I put my sensor, and based upon that I'll be collecting my training data. But yes, that will take some time to generate those training results.
Okay, so would you be doing it experimentally?
No, experimentally, currently, it will not be possible. But this theoretically, I'll try to see how my network works, and based upon that, I'll try extending further. The project will go further.
Okay, okay, got it.
So currently, it's fully theoretical.
Okay, got it.
I wanted to ask, like, how do you take the center of this submarine?
It's just you average out all the x, y, z values, and that's it. That will give you the approximate center of that.
Okay. Like, if there is some other geometric center that we consider along like the center that you are considering, and if we consider the relation of that other center with this current center that you are considering, so maybe we can use that as the x direction or something like that, and all for all the submarines.
I didn't get your point.
Like this is like the centroid of this, right? Uh,
Yes, correct.
uh, like maybe something like I'm not exactly sure what it
Yeah.
would be, but
Mm.
some other geometric like there are like orthogonal center will be there. Some other centers will be
Okay.
there, right, for
Uh-huh.
geometric bodies. So if we can consider some other center and this current center, and
Okay.
we can consider their orientation as the property to be say to be aligned along the line joining them to be aligned along the x-axis or something like that.
Oh, okay.
So
Okay, that's an interesting idea. So
Yes.
you're saying that if you have a way to define two different centers and you kind of say that those two centers should be oriented along the x direction with one center being forward of the other, then that should fix the orientation of the submarine along the x-axis.
Yeah.
Correct? And but you will need a similar approach in the y and the z as well in order to
Yes.
really come up with a unique value of putting it there. Okay.
Yes.
But what that different type of a center will be is a big question mark. But that's a good
Yes.
idea. We
Yeah,
can
that's a
definitely
good
think
idea.
on in those directions. We can definitely.
Like in the later picture that he's showing, the in one of them the mass is aligned in the opposite direction, right?
Correct.
Yes.
So if that that center will be in either of the directions of the original center, the other center, if there is something like that.
So suppose you consider a weighted average of some sort, Manoranjan, weighted by the distance,
Okay.
instead of just the average of all the x, y, and z. Let's say we weight the points by the distance from the averaged center, and we find a new centroid point. If we look at the x, y, and z directions, but whenever symmetry comes, that will be creating a problem because they'll be at the exact same point. So for example, in this case, whenever the mast is there, so on the front and the back, you will get some distance between the new centroid, which you compute by a weighted average compared to the general average. Okay. But if you want to look in the y direction, you will not get any because both will lie exactly on the center plane. Right?
Yes, but like.
But even in that case, even if it is a mirror, it will look exactly the same, and that being the point, I guess. Right? If I mirror it about the x-axis of the submarine is oriented along the long direction of the submarine, and I were to mirror it about the xz plane, I couldn't make out the difference, right? It still would look exactly the same.
Like I mean that this mast, this mast is like extra points. So
correct.
If we are
so the
taking
mask can be. Yeah, I think there might be some truth to this, Manoranjan. I have a feeling that this is actually a good idea.
Yeah.
It might save us a lot of trouble than trying to consider higher order coefficients and other things. Maybe something to look at. We'll discuss more about this.
Yes,
Good
sir.
thought process, Vallabh.
Yeah, that was a nice one.
Yeah, that's a good idea. We'll think more about it and we'll see. I can't make out on the top of my head whether there will be any issues, but I think if we give it some thought, we can come up with something. Maybe.
Yes.
Definitely worth a shot. Good job.
Okay, sir.
All right. Any other questions, comments? On B8. So everybody understood everything of what Manoranjan was saying? Yes, no? Come on, you guys are behaving like a classroom now.
Only at the qualitative level.
Yeah, that's okay, but at least qualitatively has it been understood?
Yeah. Like this was a totally new concept. So it will take some time to understand. Qualitatively, it was a good presentation to have. Yes.
Go through. All right. Any other comments by others?
The mathematical aspect of it, I'm still trying to, even myself, I'm still trying to learn it. So, yes, these are new concepts. And yeah.
I think, yeah, I didn't fully understand the mathematical concept, but I was able to qualitatively grasp what exactly you're doing. And the examples and the pictures you've added were super helpful to understand how the math is working, or at least what you're trying to achieve.
Yeah.
That was good.
Thanks. These mathematical equations, I know it took a long time for me to understand it myself. So it will really be difficult at the first go.
Yeah, something I thought about is they're constructing these rotation matrices with Euler angles, right? Will converting to quaternions help establish some kind of
Converting to
direction?
quadrant. Okay. These all of them are in Euler's. Yeah.
Yeah, what quaternions does is it can define. It actually takes away the this thing from Euler, right? The paradox.
Singularity.
Yeah.
Yeah. But I
So
don't think what he's struggling with is the singularity itself. Although maybe you're reaching an angle of pi by 2, which is causing you to
yeah.
have
So I
a
thought that may be due to
symmetry.
the paradox. Yeah, which can be resolved by using one extra this.
It's not a bad thought either, actually.
Yeah. Correct.
Okay, yeah, it's not a bad thought. If you convert the rotation into a quaternion, then you are looking at a unique representation of a rotation which is devoid of what you call reflection invariance. But will it give reflection invariance? I'm not fully sure that will be the
Yeah,
case.
yeah. Coordinates will give reflection invariance. Every angle, I mean, every orientation is purely defined by 4 variables.
No. I know that quaternion will give you a very unique representation. The question is, the problem is not with respect to the what you call singularity. Not necessarily here. It is more so that in which direction he is aligning it. So when he's putting it at 135 degrees, none of the Euler angles are actually coming to be pi by 2. The angles are not themselves singular, so that the representation is not falling out. It's not becoming a degenerate representation. But the mirroring part will still exist, is what I feel. Because the problem doesn't lie with the singularity. He's not experienced. So, for example, the example that he's showing with 135 degrees, none of the angles actually
He's
are coming
computing
out to
the
be singular.
rotation matrix from the eigenvalues, right?
Correct.
So that eigenvectors may be degenerate.
Only if the angles are causing a gimbal lock. Only then they will be degenerate. Otherwise, they will not be So Euler angle representation doesn't fall off until you see a gimbal lock occur. Up till that point, they are valid.
Yep.
Right. So I think in the examples that he's showing, he's not looking at a point where that degeneracy is coming into the picture. But nevertheless, the orientation finally it settles down to will be 2 different orientations depending on which one it was closer to.
Okay.
Rather than a degeneracy actually creeping in. So it's not degenerate per se, but it's slightly different problem.
Okay, I'm not sure of what is exactly causing the reflection, so I can't say.
No, the reflection is coming about, you think of it in this way. If you have an ellipsoid, there are 8 possible ways that I can flip it and it will still look like an ellipsoid.
Okay.
Right? And any of those 8 are a valid ellipsoid formulation. Right? So for example, in this case, you see the most of the masked points are on the top towards the left.
Yes.
His picture, right? Can you make this full screen, Manoranjan?
Yes.
Yeah, all the points are on the top and the left. But a perfectly valid would be that if I rotated this about the z-axis by 180 degrees, it would still be a perfectly valid first order ellipsoid, still with its major axis oriented in the right direction.
Okay.
Right. So either way, the method is still right. So the question then becomes which one you are closer to. That is what is causing the problem. Which canonical orientation or which way is it closer to? So if I have the object space body at 45 degrees versus 135 degrees, one is flipping into with its mass towards the positive x-axis. In the other way, it is flipping into with its mass towards the negative x-axis. Because the method does not ambiguate between these two, it is very difficult to, you have to have more information in order to say that one orientation is different from the other.
Yeah, isn't that what quaternions do?
Quaternions will exactly do that, but the problem is not with the quaternion here itself, right? The problem is what is its original orientation and which one it is closer to.
Okay.
The problem is not that I'm facing a degeneracy. That's what I was trying to get at. I don't think I'm doing a very good job of explaining that here. Maybe I can think of a better way to do this. Okay, my basic idea here is that you see the ellipsoid there on that picture, right?
Yes.
It is perfectly possible that if the ellipsoid was flipped over by 180 degrees, it will still be an ellipsoid, isn't it?
Yes.
And both of them are possible outputs of the method. When you want to say that I want to orient the major axis of that ellipsoid along the x-axis, I can put the mass towards the positive x-axis or I could put it towards the negative x-axis. Correct?
Yes, that's it.
And depending on which way I put it, I'll come up with the different values of those rotation invariant descriptors that he's talking about. Right?
Yes. So I thought of quaternions. Yeah. So I thought of quaternions because we faced a similar problem when doing one of the courses, and how Sir explained it was by using quaternions.
And you're right that when you have the quaternions, then it's a very unique representation.
Okay.
But here the method should give you the unique representation. Here the method itself has 8 different possibilities which it can give. And which one it will go closer to, there is no knowing ahead of time.
Okay. Will formulating it initially in quaternions help?
Don't know. I don't know the answer to that.
Okay.
Okay. All right. But that's a good thought process. All right. Any other thoughts? Okay then. So then we'll stop recording at this point.